This video is primarily to cover material in Chapter 9 that we're not going to have time to go over in class. Basically, I feel like this chapter gives you a lot of separate pieces of background information that are nice to know, but not all of it is crucial to your understanding of later chapters. But I want to try to hit the highlights in this video so you don't feel like you're missing out, and so that you do have a good background or foundation of information, or instead of information, maybe of knowledge. So we're finally going to let our charges move, and we're going to start talking about current. We're going to look at circuits where current is flowing and be able to analyze them. And so this is sort of a shift from what we did in the previous chapters, which really all fell under the category of electrostatics. And now we're going to allow that current to move, let the charges move. So what do we mean by current? So in this picture, and as well as some of the expressions, there's some background information for you to know. So in general, current is the flow of charge. And so in this picture right here, we see all the different little charge carriers moving through that volume. And when we're trying to measure the amount of current that we have, we want to know what is the total amount of charge that would sort of pass by this cross-sectional area that you see here, the shaded little circle, per unit time. So the average current is just the change in current over the change in time. And again, we can sort of choose some particular benchmark or finish line, and we're watching the current go past that line. In this picture, it's that cross-sectional area of what is imaginary of a piece of a wire. So we measure current in amperes. We usually just call them amps. So the letter that we use to talk about the current is just capital A. And that represents a current a coulomb per second, because charge is measured in coulombs. As you might see with, like, when we talk about average value, there can also be an instantaneous value of current. There's not a lot of different situations where current changes. Primarily, the only circuits that we'll be looking at where the current changes is RC circuits, but usually when we're talking about a circuit, the current will be constant. In the cases where the current can change over time, it might be useful to think about the instantaneous current, which is the derivative of charge per unit time. So I just want to do a really simple example using the definition of current. So in this problem, we're asked how many electrons flow through a point in a wire in 3 seconds if the current through the wire is 4 amps. So this question is using our definition of current, which is delta Q over delta T. And so the first thing that we want to know is we can actually calculate, given the information, we could calculate the total charge that passes through the wire. So we would just rearrange this, and our current is 4 amps, and our time is 3 seconds. And so if we multiply those together, we get 12 coulombs. But that wasn't actually the question that they asked. They actually asked how many electrons that would correspond to. And so we have to remember from earlier chapters what the charge on an electron is. And so 1 electron is 1.6 times 10 to the minus 19 coulombs. And so you can see we're going to get a lot of electrons. And if we do our math, the number is going to turn out to be 7.5 times 10 to the 19 electrons. And so just a really simple example of how we might interpret this definition of current. There's also a convention that we use for the flow of current, which might seem kind of weird. And so I want to explain it. We spent a fair amount of time when we introduced electrostatics and talked about conductors and insulators to say that electrons are the particles that are moving around when something acquires charge, whether it be positive or negative charge. It was always because there was an excess of electrons or a deficit of electrons, because they were the things that were free to move in the atom. And it's still true that the electrons are what are free to move in the atom. And in fact, when we're talking about current, and current occurs when we have conducting wires and we are allowing the electrons to move, because metals have those free electrons that they can allow to move through the material. We know that when the current is happening, that it is the flow of electrons. But the convention that we use, and I'll explain why we do this in a minute, is that we're going to say that the direction of the current is the direction that a positive charge would move. And so in this first picture, you can see a piece of a wire, and you can see all the positive charges, they're moving to the right. And you can also see that that's the direction of the current and the electric field. And so the bottom line is that we sort of use the direction of the electric field to define the direction of the current. And so the fact that those two are to the right is why the fact that those are to the right is because we're defining the current as the direction that a positive charge would move in the electric field. In the end, we're going to talk about or see that the reason that the current does flow in the first place is because there is an electric field set up in the conductor, the wire, and that creates a force that causes the charges to want to move. The second picture right here is showing actually what a more realistic value or realistic picture of what's going on is, but you can see the negative charges, because the electric field is directed to the right, the force on the charges is Q times E, but Q is negative, so the force ends up being in the opposite direction from the electric field. So in this picture, because we're showing the direction of the negative charges, they're actually moving to the left while the electric field is directed to the right. But the direction of the current still remains to be to the right. So, bottom line, when we talk about the flow of current, we should always think about which way would positive charges move in a circuit, and that will be the direction of our current. And when the charges are moving, I think that there's this misconception that these charges are moving super quick. And it's not actually true, which can be kind of confusing, but if we start to think about it, it can make sense. I think part of the reason that we think of current being really quick is just thinking about the response time that we get when we turn on a device. Like, say you walk into a room and you turn on the light switch, lights come right on. And so I think that there's this part of us that imagines the electrons that were at the switch having to travel to the light before it goes on. That's not exactly what's happening. When we turn on the switch, we set up an electric field in the wires, and all of the electrons are going to start to move all at once. And that's what's going to cause the current. But an individual charged particle is actually not going to go that fast, because this is the path that a charged particle might actually be following, as while it feels a force that wants to cause it to move with the electric field, as it's moving, it kind of does what we call a random walk, because it will bump into another charged particle. That collision might cause it to change direction. And so you see that it's actually quite of a zigzag path that it ends up taking, which is not very straightforward. And the reason, again, is because of all these collisions that happen as it's trying to move with the electric field. In the end, the speed of the charged carriers that cause the current is actually usually pretty slow. In fact, a typical value of drift velocity, which would be the speed of the charge carriers that are moving when there's a current, is usually around some sort of millimeters per second. So it is pretty slow. But the reason that we see such an instantaneous result when we turn on the lights or turn on any sort of electrical device is that all the charges start moving at once. And so that would account for also the charge carriers that are very close to the point where you would, activate your device. They move, and so the response is almost instantaneous. It doesn't have to be one particular charge carrier that starts at the switch and travels to the light to make it go on. They all start moving all at once. So keeping that in mind, we want to come up with an expression for current, which helps us to understand all the factors that are involved in creating the current. This is an expression we'll see. You might have a few problems using this. In the end, we won't really use it too much, but it's just kind of given us sort of a model of how we think about current in a conductor when it's set up. So we're going to start off with the definition of current, which is just delta Q over delta T. And there's a couple things that we're going to have. We're going to talk about the number of charge carriers per unit volume. We're also going to talk about Q, which is the charge per carrier. So, for each, whether it be we're visualizing it as a positive charge to go along with the model of the current or an electron, how much charge does each one of these carriers have? And so that's going to be a key of calculating a new expression for this current. So let's look at this picture. Again, we're imagining just taking a small piece of a wire, and it's going to be a cylinder, just to make it simple. And what we want to do is we want to imagine, so we have sort of this cross-sectional area here, and what we're going to do is we're going to imagine starting my stopwatch and allowing a certain amount of time to pass by. In that amount of time, a certain amount of charge carriers will pass by that magical sort of start line, and however much charge passes through that will be the total amount of charge. And then when I stop my stopwatch, that will determine the amount of time. Now what's going to happen is if we imagine we started our stopwatch right here, if the average speed of a charge carrier is equal to its drift velocity, the distance it'll travel in the amount of time that I have my stopwatch running will be that speed times the time. So that's why this horizontal thing is labeled as the drift velocity times the time, because that's how far they're going to go. And then anything in this sort of shaded region between the beginning and the end, any charge carriers that are in that volume are going to be contributing to the current, because all of them have passed by the starting line, which is right here, in the amount of time that I had on my stopwatch. So the total amount of charge that I'm going to have is going to be equal to the number of charge carriers per unit volume times the charge that they each have, but then I have to write an expression that talks about the volume. So I might just call this volume right now and do another step, and then this is delta T. So what is the volume? Well, the volume is the volume of this shaded cylinder right here between where we start the stopwatch and then when we end it. And so that has a cross-sectional area of A, and then the height of that cylinder is the drift velocity times dt, and then I divide by dt. And so in the end, our expression for the current looks like this. So the current that we get in this model is related to how many charge carriers I have per unit volume, the charge that each of them has, the drift velocity, and then the cross-sectional area of the wire. And so this is an expression that sometimes is used when we're thinking of the sort of atomic model of current. This is the expression of how we express current. This absolutely is equal to delta Q over delta T, which was our first definition, but it's just a different way to express. Okay, so I just want to remind you of the expression we came up with just in the last slide. So it was current was equal to the density of the charge carriers, the charge per charge carrier, the drift velocity, and the area. Now we're going to introduce a new term, and it's called the current density. And we use the term J to represent the current density. And here, what is, I think, a little bit unexpected, the current density is defined as the current per unit area, because you're thinking about, again, in this sort of model of the wire, we're thinking about the current passing through this cross-sectional area. So I know that usually density is a measure of something per unit volume, but for current density, it's the measure of current per unit area. And so again, we use the letter J to represent that. And if we look at this expression and divide by A, we can see it's equal to NQ times the drift velocity. So that's something to know, but one of the things that, the reason we introduce current density is we're going to actually use it to come to Ohm's Law, and an Ohm's Law that we're going to use a lot in coming chapters. And so the first thing that we're going to say is the current density is always in the same direction as the electric field. And so J, I should put like sort of a proportional, is proportional to the electric field. And we're going to write them both as vectors. We're going to kind of come up with a relationship, and then we're going to call this Ohm's Law. So let's get to that. So Ohm's Law comes up when we talk about that relationship between current density and electric field. And so the way that it's usually written is that the current density, oops, the current density, so if you remember in the last slide, I said that the current density was proportional to the electric field. When we have a proportionality, we need some sort of constant to make it an equation. And the two proportionality constants that we can choose from are either called the conductivity or the resistivity. The conductivity is a measure of how likely a certain material is to conduct electricity, like how, if it has a high conductivity, it's going to be very easy to get electricity to flow in that material, and then if it's low, it wouldn't be. So sigma is the conductivity. Resistivity is really sort of looking at it from another viewpoint, like resistivity is like how much does it fight the flow of current. And so resistivity and conductivity are inversely related to each other. In your book, you'll see that there's a table values for conductivity and resistivity for different materials. So the values for sigma and rho are going to be characteristic of a material. Like there'll be a constant for that material. So in any case, this is one way that we write Ohm's law, in that the current density is equal to the conductivity times the electric field, or we could say it's equal to the electric field over the resistivity. Another way to write it, as I say here, is the resistivity is the ratio of the electric field to the current density. And you can see that that's just rearranging this expression up here. And so not all materials behave this way, but we're going to focus on materials that do. And so in materials where the current density and the electric field are related in the ways that we see here, are said to be ohmic materials. And so when they obey Ohm's law, the material is ohmic, and we're going to deal with that kind of material when we study our circuits. Write Ohm's law in a way that's going to be more useful for us. So we're going to have this, this is the sort of the setup that's going to allow us to get there. So the idea here is we have a battery, that's what here, so that has some potential difference that it's going to be providing. And we're going to attach it to a length of wire. And so the potential difference across that wire is equal to that of the battery. Connecting this piece of wire to a battery will set up not only a potential difference across it, but an electric field within the wire, within the conductor. And also, of course, it'll cause a current to flow and also current density. I want to note here that if you think about it, as the current is shown going from left to right in this picture, notice that that is accounting for positive charges would come out of the positive terminal of the battery and move around in this manner. Again, using that convention for how positive charges would move in a circuit is the way that we're going to say that the current is moving. Okay, so let's look at this. So I have some change in potential across that, across this piece of wire. And that's equal to the electric field times the length of the wire. But we also had said that the current density is equal to the conductivity times the electric field. So let's use that to replace for the electric field. So we have delta V is equal to J over sigma times E. I'm sorry. Yeah, I substituted for E. Right there. Times L. So I substituted J over sigma for the electric field. Just made a little mistake there for a moment. The current density is the current over the area. And then we're going to put all these terms together here. So what I did is I just sort of grouped things a little bit differently. So I had substituted in for current density, current over area. I put the current by itself and everything else off to the side. And I also said that 1 over the conductivity was the resistivity. And now, if we put these three terms together, the resistivity of the wire material, whatever it was made of, and the length of the wire and the area all play a role in what we would say would be the overall resistance to the flow of electricity of the piece of wire. So it depends on the resistivity of the material, how long the wire is, and its cross-sectional area. And so we just replace that by the overall term of resistance. We measure resistance in ohms, and we're going to use a capital omega as the symbol for ohms. And so basically what we've gotten to is the Ohm's law that we're going to use a lot moving forward, which is V equals IR. So that's the last thing that I wanted you to think about, at least for this video. I have another video that talks about power in circuits, and so you want to also know that material, and that will really cover everything in chapter 9 that will just help to give you a foundation for current as we move forward with our circuits.